So we're gonna continue the video. Sorry. Uh, so we're gonna continue the video on probability and statistics for IB, which I think we ended on standard deviation. Just to sort of do a recap, standard deviation was just sort of like if you have like random points of data like this, and let's say each of those points of data are sort of like oscillating around the mean, which is the average point of the data, then we want to know sort of like what's the average deviation. This deviation might be minus 1.5, and this might be plus 1, and this might be plus, plus 0.5. And in this case, the average deviation is about like 1 maybe, like you have 0.5 or 0.5. Or actually like it's probably about like 0.5 or 1.5. But what you have to understand is that the equation had a squaring component to it because we don't want to deal with the negative numbers. We just want to have like sort of like the absolute deviation from the mean. Therefore the equation sort of looked like this, where this is like sigma, and it was basically this, very intuitive equation, it's like you have like x, the summation of x minus the mean squared divided by n, which for some reasons sort of like reduces to this, which is another way of just writing the same thing, which is standard deviation. You can also find it via this equation, which is the summation of each term squared divided by the number of terms in a series in the set, and you want to do minus the mean. And then you want to square root all of that. So this is like quicker because you have one less operation to do. You don't have to do subtraction. You can just sort of like go ahead and like square each value and sum all of them up, divided by the total number of values minus the mean squared. I'm just going to check the camera. Okay, good. Okay, so now we're going to get into like the actual statistics, because these were sort of like just definitions. And the first thing that we're going to talk about is permutations and combinations. So this is like 2a permutations and combinations. And all you have to sort of think about for this is, first of all, the notation is this, NCR, and this is like NPR. It's sort of like how it's notated. And, you could write it with the uppercase N, or you could write it with the small case N. It's really the same thing. It doesn't really matter. C for combinations, P for permutations. And what you have to understand is combinations, the order does not matter. Order does not matter. Order does not matter. And here you have to sort of understand order does matter. Order does matter. So basically, combinations, the order does not matter. Permutations, the order does matter. And how can we think about this conceptually? Well, suppose you have a number of objects. Let's say you have 2 circles and you had a box, and you had a triangle, and you want to put them in a container like this, and let's say you had like, the box, the square box, and let's say you had like the triangle, this is a combination of things, it's like ingredients. They mean something together, a square and a triangle give you something else, it's like a chemical reaction, it's a combination. The order does not matter, if I put the triangle here, it's the same combination of ingredients from the point of view of conceptually what's in the container. And the container, we might call it R. And, in this case, R equals 2. R always designates the total number of elements of the set that are considered to be a combination, And permutation is just a special case. This is actually a special case of combinations where the order does matter. Like think about this. Like if you want to think about like n numbers, and here n equals 4. In this case, n equals 4. And having n equals 4, you want to know, okay, how many ways can I order this thing? And if the order does not matter, there's only a few ways to do this. It's like 6 ways maybe. You want to like have like circle A, circle B together with the box, and then this with the thing, and then this with the thing, and so on. But see, just for this combination, let's say this box is a box and this is a triangle. Well, if I revert the order, then that's already 2 more additional combinations that's allowable. So you can see that permutations is going to have way more options because the order does matter, and combinations is going to have less options because the order doesn't matter. So if you have them in the box, no matter how you arrange them, it counts as one option, and the equation goes like this. The equation goes like this. So you have n factorial over n minus r factorial, and n minus r factorial, and it sort of goes like this, this is the equation. And this is sort of like how you want to think about this conceptually. And PR, which you could write sort of like in a different way. But this is the equation of how you find the permutations. The number of permutations for a set of n total elements, and you want to know permutations of r number of combinations where like r equals 2. Maybe you have a box of 3 and you want to see, okay, how many arrangements of 3 can I do with like this total number of n equals 4 objects? And then in this case n equals 4, and then r will be equal to 3. In this case r is equal to 2. And combinations, you want to use just the following equation. It goes like this. It's actually the exact same equation. The exact same equation. It's the exact same equation, but you want to divide it by r factorial. It's going to be like n minus r factorial, and it's going to be times r factorial. Sort of goes like this, And the way to remember this is, one, combinations is you combining things, the order doesn't matter. Permutations is sort of the language of like cybersecurity and codes, and the order is very important for a password, So permutations, the order does matter. Combinations, the order does not matter. And combinations, there's way less options than permutations because the order does matter. And you have to think about the combinations is going to be a smaller number, so you divide by this extra r factorial. And you know that if the denominator is greater, then the entire number is going to be less. So this is combinations and permutations. And we'll check the camera. Cool. Okay, now the next thing that we're going to talk about is the binomial distribution. And the binomial distribution is basically this. This is the binomial distribution. And the way it goes is very easy. It's, it's a type of distribution. Distributions are sort of like statistical, sort of like type of phenomenon. And you might have the binomial distribution, which is a type of phenomenon which applies to a type of natural event, which have an element of random, and therefore you want to use probability because it's random. But you might also have Poisson distribution and different kinds of distribution. The binomial distribution has the following characteristics. One, it has n repeated identical events. N repeated identical events. N repeated identical events. Identical events. And a way to sort of think about this is like, okay, maybe you want to flip coins. I'm going to flip coins n times, and it's the exact same flip from the exact same sort of like gravitational center, and the event is identical, and it's repeated n number of times. The number n is the number of attempts or a number of trials, and number two, you have a binary outcome. You have a binary outcome. You have a binary outcome. So it's either, A, outcome A, or A naught. A or A naught. Or it could be yes or no. Or it could be heads or tail. So anytime where you have a binary choice, a binary outcome for a number of events, a certain kind of event, then you might want to apply the binomial distribution. And, okay, so these are sort of like characteristics. Okay, so we have like binary outcomes, n is the number of events, and basically, for n events, P is the probability of success. P is the probability of success, and Q is the probability of failure. So, it doesn't mean much. What it means is like A and A naught, for example, and where P equals Q, P plus Q equals 1, because something is going to happen, it has to, equal to the, that something is going to happen. 100% something is going to happen, so that P equals Q is equal to 1. One of those things is going to happen. Together, they're the total set of, possibilities. Okay, so P is success, Q is failures, and it's going to be defined as such. And n is the number of events. Then the probability of, so here's the question. You want to ask this question. What's the probability that during n events that P is, that there's going to be x times successes? X times successes. What's the probability? What's the probability P of x that there's x times successes? What's the probability? And that probability goes by the binomial theorem. It sort of goes like this. Well, we're just going to use the whole board and remind these values sort of like later. And where P is like A, Q is like A naught. This is success, this is not success, which is failure, which is just like one minus the other. And P of x, which is the probability that during n trials, there's going to be x times of success. The probability goes like this. N of x to the x and multiplied by q to the n minus x to the n minus x. So this is sort of like how it goes. So this is like really the equation, and you know, if you want to find a probability that during n attempts there's going to be x successes, this is how it goes. And where this is like NCR, and we just looked at its combinations where the order, you know, does not matter because it's just combining things. And you can find it by the previous equation that we just looked at. And in this case, n is n and r is x. So you just have to sort of fill it out. I'll just check the camera. Is it recording? Okay, it's recording. Okay. So now we're going to look at the Poisson distribution. The Poisson distribution. So the Poisson distribution is basically another kind of distribution, you know, it's random events. And the Poisson distribution was to sort of motivate this. It applies to, you know, the number of mutations in a strand of DNA, in a DNA strand, during time t, you know, or units of time t, you know, this is something really random, you know, but the Poisson distribution applies because it's this kind of phenomenon. You have to sort of think about this. There's different kinds of sort of like events, and they have probabilistic rules, and some events obey certain probabilistic rules, and that's really it. And you might apply the Poisson distribution in the case where the occurrence of natural disasters. And you might also apply it to the number of customers at a store at a given time. And you know, if you think about this, these are all random events, and they just happen to follow the Poisson distribution, which means it's a very powerful tool for predicting random outcomes. And it doesn't apply to everything, but in the case where it does apply, you know, if you're a scientist and you're looking at something random, you might want to check if the Poisson distribution applies, and if it does apply, then it's going to be a good predictor for the probability of stuff happening in a given amount of time. Like, this is always specified within a specific time frame. And the Poisson distribution sort of goes like this. It's a function f of x and lambda, and it goes like this. You have lambda of x, which is multiplied by multiplied by the natural number to the power minus lambda divided by x factorial, and this is the equation. Okay, and you know, we have to describe this equation and sort of like define the terms. Lambda is the amount of like events, or the amount of like attempts. So this is the average number. This is actually the average number of occurrences. Average number of occurrences. of occurrences during t, during time t. So you have to sort of think about, okay, this is something which is known. You know, we know that usually in an hour we get on average 3 customers at you know, T-Mobile, and basically you want to know, okay, what's the probability that given this average for the time t, which is like 1 hour, what's the probability that I'm going to get X customers, you know? Because the average is an average value. Sometimes it's going to be more, sometimes it's going to be less. You want to try for a number X. So X is like number, X is value being checked for. Being checked for. So you're sort of like a doctor and you're evaluating the probability of, you know, a certain probabilistic outcome. And this probabilistic outcome is you want to, there's a deviation, and then this deviation is probably can be calculated by, you know, lambda minus x, you know. But you just want to know, okay, given this average, you know, what is the probability that I'm going to get this particular deviation, you know, which is a particular number, a particular value, which is possible because it's random and it's going to fluctuate around an average, which is lambda, but it's not always going to be lambda. And if it's you want to check for x, then this is how you check the probability that, you know, during an well, actually, like, okay, so a better way to explain this is like the event is going to occur lambda times, and you want to know, okay, if it occurs lambda times, what's the probability that x times is going to be a particular outcome, you know? So x is the number of particular outcome, you know, when maybe you have like a and you have a naught, and you want to know, okay, what's the number x times that you're going to get a out of like lambda times, you know, where lambda is sort of like the average number of things that are sort of like supposed to happen during an hour. So that's sort of like, you know, this is an average value which is expected, and you want to check for x, and that's basically it. And what you sort of like have to look for is that they're telling you in the problem, you know, in IB Math HL, if they tell you in the problem, the Poisson distribution applies to this sort of problem, the average sort of like number of events during time t is lambda, okay, what's the probability that it's going to occur like x times, okay, then now you know you have to use this equation in this particular way. And I'm pretty sure it's in the IB formula book, and you just have to apply it. And it's going to give you a probability that the event is going to occur like x times. The particular event that you're trying to check for, you know, during time t, given an average lambda. Okay. So now we're going to look at, let me just check the camera. So now we're going to sort of look at, we're just going to look at Bayes' theorem. And it's very easy. We're going to look at it like very intuitively. So this is like section 3, which is like Bayes' theorem, you know, and that's going to be the last thing we're looking at. And I really wish we would have time to sort of like look at examples. We'll try to see like how each of those things apply. I do have an example for binomial distribution, so we'll try to look at that. And in Bayes' theorem, we'll be like sort of like very literal in sort of like how we come up with the theorem. So let's say you have like 3 things that could be happening, you know, where each of those things have a probability of 1/3, you know. And let's say like this is like P of A, okay. Well, let's just sort of like name the branches first. This is like A1, this is like A2, this is like A3, okay, and each of those things sort of like has a binary outcome, which is like B and B naught. It's like B, and this is like B naught, and this is like B, and this is like B naught, and this is the same thing, binary outcome. Okay, and then it sort of goes like this. And the Bayes theorem is basically a conditional theorem. It's a conditional probability of a cause given its effect. So it's sort of like reversing a thing. It's like knowing B is basically saying, we'll sort of like write it linguistically before we write the equation. Knowing B has occurred. Knowing B has occurred, what is P of A?